We are continuing our discussion concerning the principal axis of transformation. Again, to remind you, we're really drawing heavily now upon what we did in some previous videos, videos 17 and 18, when we learned how to diagonalize matrices. Video 26, we talked about similar matrices. In video number 25, we talked about symmetric matrices. That is, when you have a matrix, you take its transpose and still end up with the same matrix, that for those symmetric matrices, their eigenvectors are orthogonal. We'll make use of that in a few moments. And then in videos 27 through 32 is when we talked about orthogonal matrices and their special properties. And then finally, the last two videos, 33 and 34, we began our discussion concerning the principal axis of transformation. And let's just review some of the highlights of that. We're trying to go through it carefully because it's such an important topic. Remember how we have this set up, that we have an XY coordinate system. We have two different vectors. One we label small r, one we label large R. And then we have a primed axis system. The x prime and the y prime are perpendicular. So the primed axis system, we can think of it as just taking our unprimed system and just rotating it by an angle theta. And we were saying that as we began this kind of discussion back in video number 27, that there's a matrix that relates vector small r to vector large r. So if we know an xy point in small r, the matrix will tell us the corresponding xy point in large vector r. Then for our primed axis, there is a matrix that if we have an x prime, y prime point, it will tell us a corresponding xy point. So, for example, if we're on small r and we know an x prime, y prime point, then the matrix C will tell us its corresponding xy point. Or if we're on large R and we know an x prime, y prime point, the matrix C will give us its corresponding xy coordinates. And as we derived in video 28, with this type of setup, the matrix C that transforms an x prime, y prime into an xy y point, that matrix C is this. We derived that, I think it was in video number 28 or video number 29. And since the effect of this matrix is just to rotate the unprimed axis into the primed axis, then the matrix that, again, takes an x prime, y prime point and transforms it into an xy point, that matrix is sometimes then just called the rotation matrix. And notice that this rotation matrix, what we call C, this is an orthogonal matrix. This column vector is a unit column vector, so is this one, and these unit column vectors are orthogonal. If we took the dot product, it'd come out to 0. So we have two orthonormal column vectors here. That's the definition, then, in fact, of an orthogonal matrix. We'll come back to that point in a moment. Now, what we know how to do, then, with these equations here, again, this one tells us if we know an xy point on small vector r, it'll give us a corresponding xy point on large vector r. And these here take x prime and transforms it into xy. So if I'm on this vector and I know an x prime, y prime coordinate, then I can figure out what is the xy coordinate. Same thing here. That's what these equations are. What we don't know right now is this. Suppose that I know an x prime, y prime coordinate for r, and I want to know what would be the corresponding x prime, y prime coordinate for a large vector r. And that's what we derived in the past two videos, actually. We're still reviewing this, and the way we did it was quite straightforward. We have this equation where large r is this, so we substitute that in, and that equals the matrix P times small r, but small r is this. So we write that in here. Whether the rotation matrix is this or something else in a different system, both matrix P and matrix C have to be non-singular. They have to give unique values. So matrix P and matrix C both have inverses. Multiply both sides of the equation by C inverse, and we get this expression. So here this tells us then, if we know an xy, y prime point on small r, that gives us a corresponding x prime, y prime point on large r. But to do that, we have to multiply these three matrices together. And that is called this P and C are called similar matrices of each other. Again, we discussed that in video number, I think that was video number 26. But let's just talk about the rotation matrix C. We just said that it is orthogonal. One of the properties of orthogonal matrix is the inverse of this matrix is just its transpose. So C inverse is just this. Cosine sine is now that row, minus sine theta cosine theta is now this row. And we had this equation, which is right here. But now C inverse, that's this. We have the matrix P, and C, that's this. So to get r prime, we have to multiply this matrix times the matrix P, whatever that turns out to be, times this matrix times the vector, small vector, r prime. So this could be quite a lengthy process. We'll come back to that point in just a moment. Now, remember back in video number 17 when we discussed diagonalization of matrices, we said, well, if we have a matrix A, say it's an n by n matrix, and it has an n number of eigenvectors belonging to distinct eigenvalues, so it has n number of distinct eigenvectors. They're all linearly independent, and then for each eigenvector, we express it as a column vector, and we make a matrix out of those eigenvectors. That's what we did in video number 17. That matrix we call the model matrix. And what we showed in video number 17 is that matrix A times its model matrix on the right and the inverse of this matrix on the left gives us a diagonal matrix. Everything is 0 except the diagonal part of the matrix, and those diagonal elements, those are the eigenvalues of matrix A. Each eigenvector belongs to an eigenvalue. Eigenvalue lambda 1, eigenvalue lambda 2, eigenvalue lambda n. So when we do this, it gives us a diagonal matrix, and the diagonal elements are lambda 1, lambda 2, and so forth. Again, we discussed that in a lot of detail in video number 17. Or, this equation, we actually had it in this form first, then multiply each side by the inverse of m, and we get this equation. So these two equations here are equivalent. Now, suppose, though, that our matrix A is a symmetric matrix. And now we're just going to deal with a 2 by 2 symmetric matrix. This is matrix A. it's symmetrical because its diagonal element, or its off diagonal elements are equal. So if we took the transpose of this, it would just give us that same matrix. So this is symmetric. Here are its eigenvectors, x1 and x2 with components x1, y1, x2, y2. These eigenvectors are orthogonal because this matrix is symmetric. So it might look something like this. This is x1, perpendicular to it is eigenvector x2, and this has components x1, y1, this has components x2, y2. And we're forming a model matrix with them. And the equation that we have in general form, that we talked about in a lot of detail in video number 17, is that our matrix A times the model matrix equals the model matrix times the diagonal matrix. So that's what we have right here. The matrix times its model matrix equals the model matrix times the diagonal matrix. Everything is 0 except the diagonal, and what comprises the diagonal in this case are just the two eigenvalues of our matrix here. Now, because this matrix is symmetric, and then we not only dealt with the eigenvectors x1 and x2, but we divided each one by its length so we can get the unit eigenvectors x1 and x2, so that these here are unit vectors and they're orthogonal to one another. They have to be because this is a symmetric matrix. We proved that back in one of the earlier videos that for, I think it's video number 25, with a symmetric matrix, its eigenvectors that belong to distinct eigenvalues, they have to be orthogonal. So these, what we have here then are two orthonormal column vectors. We have a unit eigenvector here, a unit eigenvector here, so they have magnitude 1, magnitude 1. They're orthogonal, so these are orthonormal. So this is an orthogonal matrix. And of course we have the same one right here. So in this case, the M matrix, the model matrix, is an orthogonal matrix. Now we had it written like this, in this form. Well here, since in this particular instance the model matrix is orthogonal, its inverse is just its transform. So the inverse of this would be x1, y1 as a column, x2, y2, this column as a row, and the second column forms the second row. This times this equals the diagonal matrix. So the point is that if this is a symmetric matrix, then for its model matrix, this is real easy to take the inverse. It's just the transpose of it. Okay, and again, that's one of the properties of orthogonal matrices, that when you have an orthogonal matrix, say G, if that's orthogonal, then its inverse is just its transpose. And we proved that, I think it was in video number 27. Okay, but now we have something else to consider. Let's go back and let's say that this matrix P that transforms small r into big R in the xy coordinate axis, if this matrix is a symmetrical matrix like this, then its eigenvectors are going to be orthogonal. So in that case, the primed axis system could be comprised of the eigenvectors of this. Because if this is symmetric, and we're doing with a 2 by 2 situation now, we're in two-dimensional space, if this is symmetric, it has two eigenvectors that are orthogonal to one another. So this could be perhaps eigenvector x1. This could be eigenvector x2. Just like we have demonstrated right here. Eigenvector x1, the next eigenvector x2 has to be orthogonal to it, like this. Now, when we discussed this in the last video too, here we have eigenvector x1, eigenvector x2. Here is the unit eigenvector x1. Here is the unit eigenvector x2. Now, for that situation, x1 and y1, they're just the cosine of theta and the sine of theta, respectively. x2 and y2, they're just minus the sine of theta and the cosine of theta, respectively. And how it comes out like that is very straightforward. If this angle is theta, then this angle right here has to be theta. This is 90 degrees, so if this is theta, this angle is 90 minus theta, so this one has to be theta. But now, what that means is that here, these are the components of eigenvector x1. x1 and y1. Here are the components of eigenvector x2. x2 and y2. Right here. And that's our Model matrix, M. But we could also write this as cosine of theta sine theta, and here minus sine theta cosine theta. So whatever angle this is, take the cosine and you have x1, take the sine, you have y1. But look at what this is. This is this. So the point is that when you have two orthogonal eigenvectors, and you're always guaranteed orthogonal eigenvectors when you have a symmetric matrix, when you have two orthogonal eigenvectors and you take the unit eigenvectors, the Model matrix that we make is the same thing as the rotation matrix that we were calling C. So what we have here then if our matrix P right here is symmetrical in general form like this, we have this kind of an equation, but this here, the Model matrix, is the same thing as the rotational matrix C. So we have, this is P. The Model matrix is the same thing as the rotation matrix C. This is just the inverse of it. And this is just diagonal matrix, where the diagonal elements are just the eigenvalues of this matrix P. So what we have here is that if this matrix is symmetrical and we use its two orthogonal eigenvectors to form the x prime y prime axis, then this equation right here, which we had written out in a much longer complicated form, if I can find it, we had it written out like this. Well, now here then, all of this is just simply the diagonal matrix. So then we have a real simple equation now. R prime equals the diagonal matrix times small r prime. Much, much simpler system. And how can this happen? It can happen if this matrix is symmetrical and we use its two orthogonal eigenvectors to form the x prime, y prime axis. If we do that, then this is just the diagonal matrix, and we have a much, much simpler equation to work with. That is why this is the principal axis of transformation. If we're lucky enough that this matrix is symmetric, and then we use its two orthogonal vectors to form the primed axis system, then this equation here is very much simplified. So, for example, suppose that matrix P, suppose it was this matrix right here. Well, let's just look at it. For that matrix, and we had this written all out. Hold on just a moment. Let's see if we can find it. Here we go. We'll come back to this in a moment. Let's say matrix P is this. Okay, for this matrix, it's real simple to determine its eigenvalues. They're 3 and negative 1. We're not going to go through the steps because it's such a trivial problem. Then, for eigenvalue 3, the corresponding eigenvector is this. For eigenvalue minus 1, the corresponding eigenvector is this. Notice that x1 dot x2 is 0. Right, this is a row vector. Here's column vector x2. 1 times minus 1 is minus 1. 1 plus 1 is plus 1. Add them together, it's 0. So we have two orthogonal eigenvectors. They have to be orthogonal because this matrix here is symmetric. Now we're talking about making unit eigenvectors. Well, this has a magnitude of the square root of 2, so divide by the square root of 2, there's our unit eigenvector. Same thing here. There's our unit eigenvector. So here is matrix P, unit eigenvector x1, 1 over the square root of 2, 1 over the square root of 2. So this would be going over 1 over the square root of 2, and go up 1 over the square root of 2. Here, minus 1 over the square root of 2, plus 1 over the square root of 2. Minus 1 over the square root of 2, go up 1, plus 1 over the square root of 2. So here are the two unit eigenvectors, x1, x2. The entire eigenvector can form an x prime axis here and a y prime axis here. So for this matrix, here are the eigenvalues, and here are the corresponding unit eigenvectors. Now we're ready for this page. Okay, here's the matrix. Here is the Model matrix right here. It's the elements of its two eigenvectors. Model matrix here, and then right here is the diagonal matrix. This is what we had written, if we can find it real fast. You have too many things to shuffle through here. This is what we had written right here. Matrix A times the let's see, we want it in this form. Matrix A times its Model matrix equals the Model matrix times the diagonal matrix, just as we derived in video number 17. And that is what we have here. Here's the matrix, there's the Model matrix, these are the eigenvalues of the matrix. These here, unit magnitude, they're orthogonal to each other. These are orthonormal columns. This is an orthogonal matrix here and here. Its inverse, the inverse of this, is just its transpose. This column becomes a row. This column becomes a row. And the inverse of this times this just gives us the diagonal matrix. But now here, what we have to keep in mind is that this model matrix right here, this is the same thing as the rotation matrix. All we're saying is that, let's go back, if we can find that paper now, right here. Okay, this was going over 1 over the square root of 2 and go up 1 over the square root of 2. So theta is 45 degrees. So what's the cosine of 45 degrees? 1 over the square root of 2. Same thing for the sine. It's 1 over the square root of 2. So this is just, again, the rotation matrix. This is P. And this is the inverse of our rotation matrix. In this case, it's real simple, just as transpose. And this is our diagonal matrix. The diagonal elements are the eigenvalues of our symmetric matrix here. So, for this particular problem, when with the vector, or the when the transformation matrix P is this symmetric matrix right here, then what we have is, just write it up here, P is 1, 2, 2, 1. Well, once we find out what its eigenvalues are, then this equation here, we know immediately what it is. We know R prime equals the diagonal matrix 3, 0, 0, minus 1. There's the diagonal matrix times R prime. Very simple. So when we're fortunate enough to have a symmetrical matrix right here, and we can use its two orthogonal eigenvectors to form our primed axis system, then here, this whole thing, this similar matrix, is just a diagonal matrix, which gives us a much simpler system to work with. So there's a specific demonstration of it. What we'll do in the following videos, when we talk about quadratic matrices, we'll see more better examples, actually, more sophisticated examples of how the principal axis of transformation can take a complicated problem and turn it into a very straightforward, simple problem to handle. So come back and join us for those videos, and we'll continue our discussion here on the principal axis of transformation.